I made you take a little quiz where I made you use the definition of derivative a few times, and that's pretty much what happens in every calculus class. They say we're going to spend a few days on this definition of derivative, and then we got to come up with something better, because if this whole course is about taking a derivative, and every time you have to take a derivative, you got to do limit as h goes to 0, blah, 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 blah. That's going to get very old very quickly. But we are going to do it one last time. And so what I want everyone to do, using this definition, so we have the limit as h goes to 0, f of x plus h minus f of x all over h. I want everyone to compute the derivative of f of x is equal to x cubed minus 2. And to make this process a little less painful, I'll go ahead and tell you that x plus h cubed is equal to x cubed plus 3x squared h plus 3x h squared plus h cubed. All right, perfect, that fit on the end. All right, so once you've completed this, do the electronic raise your hand. Okay. So now when we plug in and take the derivative, so the rest is just a bunch of algebra. So I'll get the limit as h goes to 0. I'm going to multiply this out. I already did that for you. So we end up with x cubed plus 3x squared h plus 3hx 3xh squared plus h cubed minus 2, and I'll go ahead and distribute the minus sign, so I get minus x cubed plus 2 all over h. Yay! And what happens here, and what happens pretty much in every polynomial whenever you do this, is this 2 cancels this 2, this x cubed cancels this x cubed. Like, all of this stuff better cancel, or else you made a mistake. And we are left with the limit as h goes to 0, and I get a 3x squared h plus 3x h squared plus h cubed all over h. Almost done. I see there's an h in common, so that's going to give me the limit as h goes to 0. I'm going to pull an h out, so that's going to give me 3x squared plus 3xh plus h squared all over h. And now I can cancel my h's, yay. And when I plug in h equals 0, these things go away, and I'm just left with 3x squared. All right. Now, this is the last one we're going to do. Right? Because there's got to be a better way, because this is miserable, right? And like I started with x cubed, right? This is doable. But if I said, what if this is x to the 4th? And you go, well, that's less fun. And then if I said, well, what if it's like x to the 10th? Then good luck, because nobody wants to, raise x plus h to the 10th. So what do? Well, we look for a pattern. And I know some of you probably already know the pattern, particularly if you've taken physics, because if you're in AP physics, your physics teacher probably already told you what's going on. But I kind of want to analyze what happened here. See, what happened here was brain freeze. I want to talk about what's going to happen if this was like an x to the 5th. So don't write any of this down. This is just crazy math guy talking. If this was x to the 5th, like I changed it to f of x equals x to the 5th, when I plugged it in, I'd get x plus h to the 5th minus x to the 5th all over h, and I get this limit as h goes to 0. And I have this lovely job of taking x plus h and raising it to the 5th. Well, what does that look like? Well, first of all, x plus h raised to the 5th is really big. But most of it doesn't matter, right? And here's why. See, normally if I were to raise this, the first couple of terms are actually pretty easy. going to be the limit as h goes to 0. X plus h to the fifth is going to be x to the fifth plus 5x to the fourth h plus a bunch of stuff that's not going to matter, and here's why. It's going to have something h squared plus something h cubed plus something h to the fourth, dot, dot, dot. And then I end up with my minus x to the fifth. And here's what happens. See, what happens is the x to the fifths cancel, and then everything in here has at least one h with it. Like this term has one h with it, this term has two h's with it, this term has three h with it, this term has four h's with it. And what's going to happen is we're going to factor an h out. And when I factor the h out, I get limit as h goes to 0. When I factor that h out, that's going to give me 5x to the fourth plus something with an h plus something with an h squared plus a whole bunch of stuff with h's. Why did I just say a whole bunch of stuff with h's? Well, these h's are going to cancel. And the reason these don't matter is because when they have a bunch of h's, when I plug in h equals 0, these are just going to go away. And so what ends up happening is my derivative ends up being this 5x to the fourth. So I'm going to write down just a couple of examples. Example number 1. If I give you f of x, and we said it's x cubed, we kind of found out that f prime of x is equal to 3x squared. Example number 2. If I give you f of x is equal to x to the fifth, we found out that the derivative of f of x is equal to 5x to the fourth. Okay. And I could go through a few more, right? I could say, well, what if f of x is equal to x to the ninth? Things that we noticed. One, every time we take the derivative, the exponent goes down by 1. Right? And number 2, whatever the exponent is comes down in front. So if I've got x to the ninth and I want to take the derivative of it, I'm going to have an x to the eighth because when we take the derivative, the exponent goes down 1, and then whatever the exponent is goes down in front. Now, I've done a whole lot of hand waving. Well, when you take this in college, they'll do the full proof, and if you want to see it in your book, or there's lots of places online, if you ever want to see like the official reason why this is, you can, and when I first started teaching, I would actually do that whole thing, and then what would happen is I'd get to talk about stuff for 10 minutes, fill up the board, and nobody really cares, and what really matters is the little formula at the end. And our little formula at the end is this thing. If you've got a function, let's say f of x is equal to x to the n, where n is some power, turns out the derivative is going to equal n times x to the n minus 1. And all this is anytime you take the derivative, you reduce the power by 1, which is at n minus 1, and whatever the exponent is, that goes out in front. And this is affectionately called the power rule. Why is it called the power rule? Because you're dealing with powers. They're not really creative with names. So how do we use this? Well, how we use this is we look in, let's say I give you f of x is equal to, let's do the square root of x. Actually, yeah, we'll do that. See, the power rule works with anything. Now, actually, I probably could have made you take the derivative of that. I did yesterday. But let's say it's x to the, so this is square root of x. So we're in a kind of a weird and wonderful area in that a lot of times in math, you have lots and lots of things you could do. And like if it looks like this, you do this part. If it looks like this, you do this. If it looks like this, and you have a whole bunch of, if it looks like these little variations, then I have to do all these different things. Well, for the next few days, actually for the rest of this week, you're in a very rare situation that you only know one thing. I'm going to tell you what you know. you know how to handle taking a derivative if it looks like something x to a power. That's all you know. So if you ever see something that doesn't look like this, you don't know how to handle it. Now, as we start learning things, there's going to be some other, as we start learning other techniques, there's going to be, some weird things that show up. But I'm going to go ahead and tell you now, there are no weird things for now. There's no weird things today. No weird things the rest of the week. You only know this. And so no matter what I give you, you have to make it look like this. Right? So what do we do in this case? Well, if I give you f of x is equal to square root of x, I need to make it look like x to a power. So I'm going to rewrite this as x to a power. Because square root is x to the 1/2. Well, now if I want to take the derivative, how you take the derivative, and this is kind of this was the sort of the animation that my calculus teacher did in high school, and it kind of made sense, so I'm going to do it here, is you take the exponent, you put it down in front, and then you subtract 1 from this. So if I take the exponent and pull it down in front, that's going to give me a 1/2, and then I subtract 1 from this. Well, 1/2 minus 1 is a negative 1/2. We have effectively taken our derivative. Now, you can't leave your answer this way. Nobody accepts negative exponents. And so when you have a negative exponent, you have to fix it. And all a negative exponent is, that means the thing's in the wrong spot. So in this case, this has to go on the bottom. That's going to give me 1 over, we've already got a fraction, a 1/2, just sort of extend that bar. And now this is going to go on the bottom. And so if this goes on the bottom, that's going to give me an x to the 1/2. And to finish cleaning this up, this is going to be 1 over 2 square root of x. So if this is your function, we write it something x to a power, and take the derivative and then clean it up. So, your turn. What if I give you f of x is equal to the cubed root of x? And what I want everybody to do, rewrite it. So, step 1. I only know how to handle it if it's something x to a power, so I'm going to rewrite this as x to a power. And so when I rewrite this as x to a power, it's going to give me x to the 1/3. Now that I've got a power, I can say, well, f prime of x is, take the exponent, pull it down in front, so it's going to give me 1/3 x. I got to subtract 1 from this, so 1/3 minus 1 is going to give me negative 2/3. Now we have to clean it up. No negative exponents. So I've already got a fraction, like that 1/3 is already a fraction. This guy's going to go on the bottom, so that's going to give me x to the 2/3. And to rewrite it with radicals, it's going to give me 1 over 3, and that gives me the cubed root of x squared. Oh, I probably should talk about this. I realize everybody's really good at algebra, but inevitably I always have someone that may be a little confused. When you see a fraction, do you know which number goes where? Okay.
Yeah.
Okay. So, does anyone want to hear my explanation of why the bottom number goes in the root and the top number goes for the power? Or do you already know all that? Raise your hand if you want to do the electronic raise your hand if you want to see my explanation why. Okay. I got a couple of people. All right. So, wait, does anybody want to see it? Okay. All right. So, before I talk about this, I want to talk a little bit about fractions. For example, if I gave you 2 over 3, 2 over 4, 2 over 5, 2 over 6. Right? So if I just look at these series of fractions, does everybody see that as the bottom gets bigger, the value of the fraction gets smaller? Right? So what I'm going to, my takeaway from this is the bottom number makes stuff smaller. Because the bigger the bottom gets, it makes the value smaller. All right? Well, what if I were to flip it? What if I were to do 3 over 2, 4 over 2, 5 over 2, and 6 over 2? When you look at a fraction, If the numerator gets bigger, the value gets bigger. So when I look at this, I think, oh, the bottom number makes stuff smaller and the top number makes stuff bigger. Well, if you look at, think of the number x to the 2/3. We're going to convert, we want to put this in radical form. So to put this in radical form, I know the 2 goes somewhere and the 3 goes somewhere. Well, in the bottom of a fraction, since the bottom number makes stuff smaller, that's going to be the root. And the top number makes stuff bigger, that's going to be the power.
Oh, okay.
So that's kind of my explanation of why the numbers go somewhere. And while we're on the topic of dealing with rational exponents, let's talk about computing rational exponents. So as far as computing rational exponents, I'm just going to throw out, let's say I give you 27 to the 2/3. Okay? Just an example. This is an easy one. And I know some of you may be used to having a calculator with you all the time, and so you think, well, that's easy, just plug it in your calculator. And my answer is, no, that's easy because you don't have to plug it into a calculator. It's all in how you look at it. So when you look at it, you might think, well, do I write it? Which way do I write it? I know this is a cubed root, and I know this is squared. Do I write it as the cubed root of 27 squared, or do I write it as the cubed root of 27 squared? And the answer is, they're both correct. But one makes your life a whole lot easier, right? See, if you look at the top, I don't think too many people are going to do this in their head correctly, because you got to do 27 squared, and I don't think most of you know that's 729 off the top of your head, right? And then you think, well, then what's the cubed root of 729, right? Those are huge numbers, right? So that's hard to do in your head. But let's think of this one. What's the cubed root of 27?
3.
And what's 3 squared?
9.
See how much easier it was?
Yeah.
So whenever you've got this whole rational exponent, you've got like a root and a power, you always do the root first, then the power. Just as a general rule, when you're computing, make numbers smaller before you make them bigger. Because if you start off big, it doesn't get easier. So, all right, that's my explanation of rational exponents. Again, I know it's review. You're all masters of that from Algebra 2, but I sort of feel the need to talk about it at this level. Wait, just to make sure we're all on the same page. So, I also forgot. I need to talk about what happens if I give you, let's say if I give you f of x is equal to 5x squared. I want to talk about what happens if there's a number in front. Because I did say you only know how to handle if it's a number x to a power, and I honestly haven't given you an example where it was a number x to a power, so I probably should do that. So what do? Well, here's the trick. Anytime you have a number multiplied, think of that as decoration. Right? Basically, you ignore it. So what do I mean by ignore it? Ignore it. It's just decoration. It's off to the side. You look at it and you say, well, can I take the derivative of x squared? Well, yeah, I can take the derivative of x squared. Like I think the derivative of x squared, that's going to give me 2x to the first. And, well, remember my decoration? It's still there. And then I just multiply it at the end, and so I end up with 10x. Probably a faster way is you think you multiply this times this, and then reduce the value of this by 1. But pretty much the only thing I'm talking about today, what you're going to practice tomorrow, what you're going to practice on Thursday and Friday is you're going to take derivative. And the only thing you know how to do, you only know how to handle if it's number x to a power. Okay, so how does it get tricky? What if I give you 3x over the square root of x? So everybody write that down. Okay. So first off, you ask yourself, is this number x to a power? Does this look like this? where you have a number in front, you have a single x value and a power. No, it's not, right? So you don't know how to handle this, right? That's important, right? I'm telling you, you don't know how to handle this. If you try to take the derivative of it looking like this, you'll get it wrong. Because the only thing you know how to handle is if it looks like this, number x to a power. That's it. I'm going to be saying that over and over. You only know how to handle number x to a power. So we have to make this look like this. So how does that work? Well, think of this as 3x to the first over x to the 1/2. And anytime you have x's on top of each other, you can make it a single x, because you can do, like, you subtract exponents. This is going to equal, well, 1 minus 1/2 is going to give me 3x to the 1/2. Right? Because you subtract.
Right.
All right? Now, when I look at this, that looks exactly like what I know how to handle. I know how to handle number x to a power. I've got, it's number x to a power. Now, did I say that the numbers are going to be nice? No, I never did. But I did say that you only know how to handle number x to a power, and that's what we have. So, when we take the derivative of this, well, our little trick was we're going to multiply this times this. And so I multiply this times this, that's going to give me 3 over 2, x, and then I got to subtract 1 from it. So 1/2 minus 1 gives me a negative 1/2. You can't have a negative exponent, so you've already got a fraction. We're going to write our 3 and our 2. This is going to go in the bottom, which is going to give me an x to the 1/2. And when I clean it up, I end up with 3 over 2 square root of x, and there's our answer. But the theme for today, and tomorrow, and Thursday, and Friday, is you only know this. And so no matter what I give you, you have to change it so it looks like this. Your turn. I want you to compute, and I've got this whole space I can use. Awesome. So I want you to compute 5 over 2, let's do x to the x to the 4th over x to the 1/3. And after you finish it, do the electronic raise your hand. All right, again, you only know number x to a power, and we clearly don't have that here. So let's see, to fix this, I'm going to subtract exponents, so I'm going to rewrite it. That's going to give me a 5 over 2. And when I subtract exponents, I got to do 4 minus 1/3, so I think it's going to give me x, and let's see, it's 12 over 3 minus 1 over 3. That's going to give me 11 over 3. And so now I've written it as something I can handle. Like, I can only handle number x to a power. So now I've made it look like number x to a power. Now when I take the derivative, I probably should have said f of x is equal to this, so f prime of x is equal to this part. So now I multiply this times this. That's going to give me 55 over 6 x. Subtract 1. So if I subtract 3 over 3, that's going to give me 8 over 3. And since I gave you rational exponents at the beginning, I'll accept rational exponents at the end. No negative exponents. I'm done. Never guaranteed you're going to get nice answers, right? All I guaranteed is you only know how to handle this. Oh, one more. Well, actually not one more, but one more thing about this. What if I give you 5 over x squared? Say f of x is equal to this. So everybody write down 5 over x squared. Now, I do notice there are a few people that are raising their hands instantly, and I have a feeling someone's shown you the trick, and so you've practiced this. I know AP Physics needs you to be able to take derivatives, so you may have been doing this for a few weeks now. All right, but, so what do? Well, remember, we only know how to handle it if it looks like this. And this does not look like this, right? It's got to be number x to a power. You can't handle an x in the bottom, right? Since you can't handle an x in the bottom, we have to rewrite it. So the rewrite of this is 5 times x to the negative 2. Because a negative exponent created a fraction. Well, when I rewrite this, now this definitely does look like our pattern of number x to a power. And if it looks like number x to a power, we can take the derivative. So that's going to give me f prime of x is equal to, this times this gives me a negative 10. The trick is, remember when you're subtracting 1. So negative 2 minus 1 is a negative 3. Inevitably on quizzes and tests, someone will do negative 2 minus 1 gives me a negative 1. And it's like, no, that's not how subtraction works. But I don't like negative exponents, and when we fix it, we end up with a negative 10 over x cubed. And there's our answer. Okay? So let's kind of combine all these ideas. What if I give you f of x equals 3x to the 1/3 over 5x squared. And I want everybody to find the derivative. And when you find the derivative, do the little electronic raise your hand. All right, so when I look at this, it is not number x to a power. So I have to make it number x to a power. I got the number, right? Number's not so bad. The number is 3 over 5. I'm okay with that part. But I don't have x to a power. So then I have to subtract. Anytime you have exponents over, like you have to subtract. So I have to do 2 minus 1/3 minus 2. So I end up with x to the negative 5 thirds. That's right, yeah.
Yeah.
Because I've got more x on the bottom, so it's going to be negative. So now I've rewritten it, and I have number x to a power. And now that I have number x to a power, I can take the derivative. So I end up with f prime of x is equal to this times this. Oh, everything cancels out. I get a negative 1. So I'll get a negative 1 x, and I've got to subtract 1 from this. So I end up with negative 8 over 3. Right, you can't leave an answer with negative exponents, so this is going to give me a negative 1 over x to the 8 thirds. And there's my answer. We started with rational exponents. You don't have to convert it. The only time we have to convert is if we start with radicals, we have to convert to radicals. All right, so what's next? Well, we've been taking derivatives in individual terms. What happens if you have to take derivatives of a bunch of terms? Oh, let's say I give you f of x is equal to 3x to the 5th minus 2x plus 1. So everybody write this down. And our job is, how do you take the derivative? How do you take the derivative when it's a bunch of terms added or subtracted together? And the answer is, as long as everything's added or subtracted, you take the derivative of each term. And so when you take the derivative of each term, this is going to give me, so f prime of x is going to equal, well, the derivative of this is going to be this times this, which is going to give me 15x to the 4th. Oh, I haven't given an example with, these two are, I'm going to call them the easy examples, so let's make sure that we have them. Of when you take the derivative of negative 2x, here's what I want you to think. Think of this as a negative 2x to the first, because that's what it is. And how you take the derivative is this times this is going to give you a negative 2, and it's going to give you x. When you subtract 1 from that, that's going to give you 0. And anything to the 0 power is 1, right? And so it turns out that the derivative of this thing is just going to be a negative 2. Okay? Next up, you got to think, what's the derivative of 1? Okay? Well, we've already answered that. It's been a few days, but we've already answered it. Think of 1 as a constant, because it doesn't change. There's no variable. It's a constant. And derivative measures rate of change. It measures how fast something changes. And so the really silly question is, does a constant change? And so if a constant doesn't change, What's its rate of change?
0.
0. So it turns out when you take derivative of a constant, you just get 0. So there's our derivative. But this isn't the question I wanted to ask. See, the question I wanted to ask was, what if I give you f of x is equal to 3x to the 5th minus 2x plus 1 all over x cubed? So everybody write that down. Shoot. Yes.
Is it true that there's an asynchronous day tomorrow?
Yes. Well, that was last week too. Your asynchronous work, I was about to tell all that in the last few minutes. So, I do want to sort of expand what we know. As far as taking a derivative, we know how to handle if it looks like number x to a power. That's what we know, right? That's all we know. And we know how to handle it, and we know how to handle something like this as long as we're adding or subtracting terms. And if you look, notice this looks like number x to a power. This looks like number x to a power. That's a constant, which is, we can argue it's number x to a power, but as long as it's terms where you're adding or subtracting. We don't know how to handle this. We can't handle it looking like this. So what do? Well, what we do is we're going to make it look something like this. And how we do that, anytime you see a fraction, you break it apart. And so this is going to give me f of x is equal to 3x to the 5th over x cubed minus 2x over x cubed plus 1 over x cubed. Now this still doesn't, like individual terms still don't help me. I'm still not here. But what I can do is I can simplify this. And if I simplify this, this is going to give me 3x squared minus 2x to the negative 2 plus x to the negative 3.
Oh, right, yeah.
And if I look at this, that I can handle because I can take the derivative of this term, I can take the derivative of this term, and I can take the derivative of this term.
Wait, is that this negative? Okay.
It's supposed to be a negative. I think I said negative 3, but I forgot to write the negative 3.
Okay.
And now I can actually take the derivative, and I'm going to you have to do this pretty quickly. So f prime of x is going to equal 6x. I'll end up with a plus 4x to the negative 3 minus x to the negative 4. Which is going to give me 6x plus 4 over x cubed minus 1 over x to the 4th. All right. So I need to talk a little bit about what's going to happen. So I gave you a homework assignment out of your book. The homework assignment out of your book is problems 3 through 23 odd. The last couple you can't do because I didn't talk about the derivatives trig functions because I spent a lot of time on the algebra, which is fine. It's actually, I'll pick up, so if you can't do the trig ones, that's okay. Tomorrow for your asynchronous, I'm going to have a handful of Khan Academy assignments. I'll put the Khan Academy assignments in. They will be due tomorrow, meaning if you don't have them done, you don't get credit, or at least attempt it. But the way Khan Academy works, it's like you gotta keep doing it. You gotta keep doing it if you get it right. And what you're gonna do is practice all this. It's going to be take the derivative of a whole bunch of practice here. Well, I've got 2 minutes, so I'm going to do real quick, because the ones for trig are not, and it actually deals with the pictures.
I have a question on the last one
Yes.
When you took the derivative of x to the negative third, why isn't it negative 3x to the negative fourth?
It is negative 3. Thank you. Thank you. I was worried about finishing and So your final answer is going to be a 3 over x to the fourth. All right. So in 2 minutes, and honestly, if you don't finish it, that's fine. But it turns out if y is equal to sine x, the derivative of sine is cosine x. So if you ever see derivative of sine, derivative is going to be cosine. If you have derivative of cosine x, if y is equal to cosine x, derivative of cosine x is negative sine x. And I actually kind of explained why with pictures a few days ago. I don't know if you remember those graphs. We had like the graph of sine, and I wanted the derivative of the graph. And you even told me that the graph of sine looked like cosine.
Right.
And you even told me the derivative of cosine graph looked like negative sine. So if you have trouble with those two, the Khan Academy won't have sine or cosine. What they're all about is taking a derivative, using the power rule, and the big idea is you only know how to hate the derivative if it looks like number x to a power. That's it. And the good news is that's all we're going to know for the next few days. Okay. It gets complicated when we know more stuff, but right now we only know this. So your job